This is my video tutorial to go with the projectile motion worksheet I created. Okay, so these questions are fairly straightforward, single task questions. Question 1a asks you for the initial vertical velocity if the initial velocity, the total velocity that is 13 meters per second and the angle of launch is 45 degrees above the horizontal. So I've collected the information we've been given and the information we need. Now I'm going to keep, on each of these I'm going to draw a little triangle diagram. So that kind of reminds you of your trigonometry, SOHCAHTOA. In this case we're asked for the length of the opposite side. So that's going to be SOH sine 45 equals VVI, that's the initial vertical velocity, but I've divided by 13. VVI equals 13 sine 45. And then there's a pause here while I get my calculator out and solve this. And we get a value of 9.192. That's an unrounded value, and then we round it to two significant figures and give the unit. 1b. Very similar question. The initial velocity is 130 meters per second, the angle is 60 degrees, and we've been asked to find the horizontal velocity. So the difference compared to the first question is which side of the triangle we're solving for. In this case we're now solving for the adjacent side, which means we're going to use cosine of the angle equals the adjacent over the hypotenuse, which is VH, the horizontal velocity, divided by 130, the total velocity. And again, pause while I solve my calculator. Cosine of 60 is a half, so this one's going to come out as 65 meters per second. Question C. In this case, we're again given the total velocity 22 meters per second, the angle 45 degrees. What is VH? So very similar data to the first question. This time though we're solving for the adjacent side again. So it's just another opportunity to use SOHCAHTOA and realize that it's the car. So cosine of the angle. In this case I haven't done the complete rearrangement. So what I've done is I've shortcutted to sort of the second step. So it would have been cosine 45 equals VH divided by 22, and then rearranged to VH equals 22 cosine 45. The answer is 16 meters per second. D. VI equals 78 meters per second. Theta equals 30, so the angle to the horizontal equals 30. What is the initial vertical velocity? So here's my triangle again. 30 in here. And so I'm going to be using sine of the angle. So sine theta equals VVI over 78. And sine theta equals 0.5. So this is again going to come out reasonably quickly. 39 meters per second. E. The initial vertical velocity is 65 meters per second. The final vertical velocity, yes that's right, equals 0 meters per second. The acceleration is negative 9.8 meters per second. What is t? So this is what the sort of calculation you do to figure out how high an object, or how long an object takes to get to the top of its flight, to its apex. Because VF being 0 is what happens at the apex. A equals negative 9.8 is the acceleration due to gravity. So we use VF equals VI plus AT, substitute in, simplify and solve, and then round to our two significant figure, 6.6 seconds. F. Okay, so again, VVI, so the initial vertical velocity equals 3 meters per second, the final vertical velocity equals 0 meters per second, the acceleration equals negative 9.8 meters per second. In this case it says what is D? Sorry, I'm completely wrong. I'm looking at G already. This one's actually solving for the acceleration given time and two speeds. So this is to look at what the acceleration, in this case due to gravity, rounded is. Now G, you're given the initial vertical velocity, the final vertical velocity, and the acceleration of negative 9.8. What is D? So this is how high does the object go in its flight above where its starting point. So we're choosing kinematic formulas. In this case, VVF squared equals VVI squared plus 2AD. Substitute in, simplify, and solve, and we get then get a calculator out, and we get that D equals 0.459, which we round to 0.46 meters, giving its unit. Okay, H. In this instance, we're now looking at the horizontal range, because we've got the distance, we've got a time, and most importantly, we've got acceleration equals 0, which indicates we're working in the horizontal direction, and we've been asked for the horizontal velocity. So we can use the kinematic equations. D equals VIT plus a half AT squared. Now with A equals 0, then a half AT squared is 0, so we just have D equals VIT. And VI in this case is the same, well, would be the same as VF. VI is just the horizontal velocity. So 200 equals VH times 6.7, the horizontal velocity equals 200 divided by 6.7, which comes out as 29.85 rather, which when we round it correctly to 30 meters per second. So expressed in two significant figures with the unit. I, we got VH equals 2.3 meters per second, time equals 22 seconds, A equals 0. What is D? So again, we've been given a horizontal velocity and acceleration equals 0, so we're talking about a range equation in this case. What is the range if we're given the time and the speed? So again, we can use D equals VIT plus a half AT squared. And we can let, if A is 0, then a half AT squared is 0, so it's just D equals VIT. So this is really just distance equals velocity times time. It's a really straightforward kind of way of thinking about things. If we travel at a certain speed, then we multiply that by the time we get the distance. So D equals 51 meters expressed to two significant figures and with the unit. This is question 2, just the first 5 parts, A to E. We're going to look at those first. So this just converts these into words a little bit, so it's a step forward. So what is the initial vertical velocity of an object that is launched at a speed of 27 meters per second? So that's VI is 27 at an angle of 30 degrees to the horizontal. And so we can draw our little diagram just as we did in question 1. VVI there on the opposite side, 27 on the hypotenuse, 30 is the angle in the corner. We know that it's the opposite in the hypotenuse, so it's SAW sine 30 equals VVI, the vertical initial velocity over 27. The initial vertical velocity equals 27 times sine 30 is 13.5 meters per second, which, when we round it to two significant figures, rounds up to 14 meters per second, which would be really frustrating in an actual question, but you definitely would need to keep that extra significant figure if you're continuing to use that data further. Part B, what is the initial horizontal velocity of an object launched at a speed of 270 meters per second at an angle of 30 degrees to the vertical? So same thing, draw the triangle, 270 on the hypotenuse, 30 in the corner. This time we're solving for the adjacent side, the horizontal velocity, so cosine of theta equals VH over 270. Rearrange, VH equals 270 cosine theta, and we get, what do we get? Let's see, calculator time, 233.82. Again, we're going to round this, 234. Oh, I rounded it to three significant figures for some reason. I should have rounded it to 2, which would have been 230 meters per second. Question C, what is the initial speed of an object that was launched at an angle of 30 degrees and had an initial vertical velocity of 63? So this is a kind of a backwardly calculating. So we're going to be, here's the angle 30 in the corner. I'm going to always draw this triangle just to make it straight so we can really see what's going on. So this time we have the opposite side, but we want the hypotenuse side. So SAW again, sine 30 equals 63 over VI. When we rearrange by multiplying both sides by VI, we get VI times sine 30 equals 63. We rearrange some more by dividing by sine 30, and we get VI equals 63 divided by sine 30. we do that with our calculator and we get VI equals 130 meters per second. Now you can do a sense check here. VI has to be larger than the VVI, and that's true. In fact, it's double it. So question D, what's the launch angle of an object that was launched with an initial horizontal velocity of 78 and an overall speed of 130? So it's very much a similar question to the previous one, but instead of the missing data being one of the sides, it's the angle. Here we're going to have to use the inverse cos. So we substitute for cos theta equals 78 over 130, rearrange, and of course the inverse operation is inverse cos on your calculator, and it gives you an angle which you can round off to two significant figures, 53 degrees. Okay, next question. Now we're moving into part E here. How long does it take for an object with an initial vertical velocity of 22 meters per second to reach a final vertical velocity of 0 meters per second, assuming that the acceleration due to gravity is 9.8 meters per second squared? Very much a how high does it go, or how long does it take to get there, in fact. How long does it take to get there? And again, VVF, so the final vertical velocity being 0, indicates the apex of the flight, and of course the acceleration at negative 9.8 similarly. So we're going to use VF equals VI plus AT, which gives you durations of flights. Good equation for that. Substitute our data in, rearrange, time equals negative 22 divided by negative 9.8. I think I'm just going to show those steps one at a time. So we rearrange by subtracting 22 from both sides. Then we divide by negative 9.8. The two negatives cancel out, so the time equals 22 divided by 9.8, which is 2.2449. And we round it to two significant figures, 2.2 seconds to two significant figures. Okay, F to J have some slight differences, so I've separated them out here and given you a look again at the questions very briefly. You can pause there for a moment if you need to. So the vertical initial velocity is 17 meters per second. How long will it take to reach the apex of the flight? So I've left out a piece of information. I haven't told you that VVF equals 0, but that's what the apex of the flight means. It means that the vertical velocity of the object is 0. So you should include that in your data that you've been given, and then you again just use VF equals VI plus AT and solve, substitute in, rearrange and solve, and then round to a final figure of 1.7 seconds to two significant figures. G, if an object takes 6 seconds from launch to reach the apex of its flight, what was the initial vertical velocity? So again, we're not given the acceleration, but we know its gravity, so negative 9.8 meters per second squared. We are given time to 6 seconds. We don't know our vertical initial velocity. What we mostly know is that the final velocity is 0 because it has reached the apex of its flight. That means it's not going up yet, or not going up anymore, and it's not yet going down, so that's why the final velocity is 0. So again, we use VF equals VI plus AT. We substitute in 0 equals VVI plus brackets negative 9.8 times 6. We simplify and rearrange and solve and get 58.8, which I should have rounded to 59 meters per second, in fact. H, how long will an object be in the air if it has an initial vertical velocity of 65 meters per second and lands at the same height that it was launched? So the key idea in this one is that it's not just the time to reach the apex, but it's time to reach the apex and return to the ground. And the key factor is that that time up is the same as the time down. So let's just work out one of them and then multiply it by 2. Again, reaching the apex, so VF, the final velocity, equals 0. We're given the initial upward velocity of 65. We've got an acceleration of negative 9.8. What's t? We use VF equals VI plus AT, substituting in 0 equals 65 minus 9.8t, rearrange it, and solve, and you get 6.6 seconds once you've rounded to two significant figures. That's only half the answer, because we have to multiply this by 2 to get the complete time. Now there is another way to do this where you use the time to get back to the same initial velocity but negative number. So you could have VF equals negative 65 and substitute that in and solve, and then not have to multiply by 2 as another option. Part I, what is the horizontal range of an object that has a horizontal velocity of 16 meters per second and is airborne for 7.5 seconds? Really, this is quite a straightforward question. Except what it doesn't tell you is, of course, that the acceleration in the horizontal direction is 0. So, and that's the key fact. Acceleration in the horizontal direction is 0. That gives you the additional information you need to know to solve this, because that will leave you with the first part, really, of d equals vit plus a half at squared, which is just that d equals v times t. So distance, the range, equals the horizontal velocity times the time. And that's because a half at squared becomes 0. J, if a projectile travels a range of 240 meters in a time of 7.0 seconds, what is its horizontal velocity? So horizontal velocity equals question mark, d equals 240, t equals 7.0. Again, we're going to use d equals vit plus a half at squared, but because a is 0, because it's travelling horizontally and there's no force acting, we just cancel out the half at squared term and we get the distance equals the velocity times the time. We substitute them, we rearrange, the velocity equals 240 divided by 7, which is 34.28, rounding to 34 meters per second. Okay, that was question 2. Now we're going to flip over to question 3, where we don't have, I've stepped you through the process of a whole word-based problem. In this case, the ball being launched at an angle of 30 degrees to the horizontal at a speed of 15. First part of the question, what are the vertical and horizontal components of the ball's velocity? So we can draw our triangle, or we can just remember the formulas, if you like, that the vertical velocity, no we're not, what am I going to do? I am going to draw the triangle, there we go. So we've got our angle in the corner there, theta, and we've got VVI on the vertical and VH on the horizontal, and 13 on the hypotenuse. We can use SOL to solve for the initial vertical velocity, getting 6.5, and we can use CAR, cosine of the angle equals VH over 13, rearrange, VH equals 13 cosine theta, solve with our calculator, get 11.26, which rounds to 11 meters per second, two significant figures. Part 3, what is the maximum height the ball, part 2, how long does it take the ball to reach the apex of its flight? So we ask for the time. We have to remember things here, like that the acceleration is negative 9.8, that the apex means that the final velocity is 0, that in this case we're talking the vertical initial velocity, so that's 6.5. We choose the Vf equals Vi plus At formula, substitute in, and rearrange and solve. We get T equals 6.5 divided by 9.8, which is 0.663 or 0.66 seconds to two significant figures. Now, this is an area where you should always make sure that you hold on to, in these calculations, at least one additional significant figure, so that when you're reusing stuff, you can be more accurate. Now, the time going down is the same as the time going up. That's one of just the key ideas of projectile motion, as long as you are starting and finishing at the same heights. If you're not, you can't use that idea. So the total time for the ball to go up to the apex and down again, the total flight time, part 5, it should have been part 5. I think I've got these out of order somehow, or I've missed a step here. So yeah, total time was 1.3. The total range we can do using the horizontal velocity and the time. I seem to have skipped out part 3, the maximum height. That could have been done using d equals a half at squared, using the flight time from part 2, or it could have been done with vf squared equals vi squared plus 2ad. Sorry about that. B. Here we are. Looks pretty lengthy. somewhat complicated. So a car is going to fly off a ramp that launches it at 40 degrees. It's travelling at 100 kilometers per hour. We're going to need to do a conversion, obviously, on kilometers per hour to meters per second to make our life easier. It's going to land on a similar ramp, which we're going to position a certain distance away, and in the middle it's going to go through a ring of fire. Now, so there's the diagram. I think it doesn't actually say, it says he needs to know where the ring of fire should be placed. I think, talking about height ways, I think it's going in the middle, so let's just assume that. Part 1. So there's my diagram. I drew the diagram and I didn't even really think about it, that was part of the question. Because if I'm reading a question, I'm always going to draw a diagram of what's going on. So part 2 is to do a conversion, 100 kilometers an hour to meters per second. So one way to do this is to think 1 kilometer per hour, and then just, what does that mean? Well, 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. So when we convert 100 kilometers per hour into seconds, meters per second rather, we have 100,000 meters per 3,600 seconds, which gives you 27.78 or 28 meters per second rounded to two significant figures. Again, I'm going to hold extra significant figures on my page for use later on. Part 3, what is the initial horizontal velocity of the car? This is standard soccer tire material again. So to quickly sketch the triangle, I'm actually going to work out both of the horizontal and vertical velocities. Actually, it's not part 3, so this is still part of part 2 because we were asked for the initial vertical velocity. So this is what we're doing now. This is part of part 2. So saw the initial vertical velocity equals 28 times sine of 40, which is 18 meters per second. The horizontal comes from car. The horizontal velocity equals 28 times cosine of 40, because car is cosine of the angle equals adjacent over hypotenuse. So what I'm writing down here is a rearrangement of that. Now part 4, how long will it take the car to reach the apex of its flight? So what we know about this is that the acceleration equals negative 9.8 meters per second squared. The initial vertical velocity we've just calculated as 18, although I should really use the unrounded. I think the reason I don't have an unrounded there is because it was so close to 18, it was very unlikely to make a difference. We use VF equals VI plus AT, and substitute in, rearrange and solve, and get 1.84, which rounds to 1.8, two significant figures, 1.8 seconds. V, how high should they position the ring of fire above the launch position? So we can use VF squared equals VI squared plus 2AD, or we can use the time and D equals VIT plus a half AT squared. There are numerous options for solving this because we now have 5 pieces of information. So any equation that includes the distance is now, of our 4 kinematic equations, is now a possibility here for solving this. I'm using D equals VI plus VF over 2 times T, which is that the distance equals the average speed times the time. T equals 18 over 2 times 1.84. Calculate it out. D equals 18 over 2 times 1.84, 16.56 meters, which is 17 meters. I couldn't bring myself to say that they should put 17 meters above because the car would crash into it, so I gave you 3 significant figures. That's not really acceptable. How far from the launch ramp should they position the ring of fire? So in this case, we're talking about how far has the car travelled in the time to get to the apex. So the acceleration is 0, half AT squared is 0, the distance that it travels, so that this is so I can use the equation D equals VIT plus a half AT squared. So that just gives you D equals VIT, and VI is just the horizontal velocity, and so we've got the distance equals horizontal velocity, in this case with a bit more accuracy to it, like the more accurate, not the fully rounded one, multiplied by the time. Oh, I should have used the unrounded time there as well. But it's alright because I'm rounding up. In the end, 39 meters from the ramp 2 parts to go. Flip to the next page. Now I'm going to have to be flipping backwards and forwards to get information. It's a real problem when you solve across multiple pages. How long will it take the car to reach the landing ramp from the time of launch? Well, we've got the time to get to the apex, so the time to get to the landing ramp is just the apex plus back down again, so multiplied by 2, and then round to our 2 significant figures. That was one where it's really important that you use the unrounded number, because if I'd used the rounded number, we would have got 2 times 1.8, which is only 3.6 seconds. Okay, and how far away from the launch ramp should the landing ramp be placed? Again, the acceleration is 0 in the horizontal direction, so the half at squared in d equals vit plus a half at squared is lost. And I'm just going back here to get some information from the previous slide so I don't get too confused. I was just trying to find out what vh was. The distance equals the horizontal velocity times the total flight time, and that substituted in and then solved to give, and then rounded to give 90 meters to 2 significant figures. So that is the end of question 2. Question 3, the stunt coordinator is setting up a crash mat for a human cannonball. The stunt person will be launched at a speed of 30 meters per second at an angle of 45 degrees. The crash mat's the same height as the launch ramp. What are the initial components of velocity? How long will the flight take, and where should the mat be positioned? So initial components of velocity, doing both horizontal and vertical components here, with an initial speed of 30 at an angle of 45. So we're going to do saw and car. One of the interesting things here is that sine of 45 and cosine of 45, of course, are the same, because you're talking here an isosceles triangle. The angles in the two non-right angled corner being the same means that the two sides have to be the same, other than the hypotenuse, of course. And the value of cosine 45 and sine 45 is both square root of 2 over 2, which is 0.707 if I remember right. So there's the answers. 30 divided by 1.41, or the square root of 2, and is true of both. Rounded to 2 significant figures, that's 21. Part 2, how long will the flight take? Here we're using Vf equals Vi plus At. This is where you get the idea that the final vertical velocity is 0 because it's at the apex, and then we're going to multiply by 2 because we want the time up and the time down. So Vf equals Vi plus At, we substitute in, we rearrange, we solve, we find that it takes 2.161 seconds to reach the apex. We double that to 4.32 approximately, and that gives us 4.3 seconds as our rounded to 2 significant figure value. Where should the mat be positioned? So now we are looking at the range. So in this direction, the acceleration equals 0, and we're going to use d equals vit plus a half at squared. But of course, half at squared is 0, so we just use the distance equals vit. Well, the initial velocity is the same as the final, which is the same as horizontal velocity. We substitute in the values we've got from parts 1 and 2, and we get an answer of 92 meters rounded to 2 significant figures. And I'm going to state it here properly. The mat should be placed 92 meters away. Probably the center of the mat would be nice, wouldn't it? You don't want to land right on the edge. I'm spelling mat wrong in all these. Why have I got in my head that mat is spelled M-A-T-T? That's a different sort of mat, like matte paint. Question 4. I think in this one I make a bit of a mistake, so just watch out for this as I make a completely wrong substitution later on. See if you can spot it before I talk about it. Maybe I don't do it in... yeah, I think it is probably in this question, but it might be in the next one. So, it is a straightforward projectile motion. It's very much exactly the same as 2 of the examples we've just done, except that I haven't led you through it bit by bit. So you have to know the process now. A water balloon lands 60 meters from its launch at the same height it was launched. It was launched at 45 degrees from the horizontal. What was its launch speed? Actually, this is not true. This is not straightforward. This is hard. This is a this is not just not leading you through, but this is a situation where I've given you only 2 pieces of obvious information. What are the extra obvious pieces of information we get? Well, obviously that at the apex the vertical initial velocity is, at the apex the vertical velocity is 0, the acceleration is negative 9.8 because it's a projectile motion. But what we're going to do is we're going to try and work out what equations we have. So the range is found usually from the horizontal velocity times the time, which is, and that gives you the range, and we've been given the range. So first equation, VH times T equals 60 meters. The second equation and the third equations here, VH, are equations for VH and VI in terms of, the horizontal velocity and the initial vertical velocity in terms of the overall speed and the angle, so using the car and the saw. We also know that the total time equals the time up doubled, and we can work out that the time up is the initial vertical velocity divided by the acceleration, and so VVI over 9.8, and we can substitute into that our equation for the initial vertical velocity. Now, that gives us an equation for the total time being equal to twice that, so the total time is VI times sine of 40 over 4.9. I've just labelled these equations 1, 2 and 3. We're now going to substitute equation 2, our equation for the time, into equation 1 to get VH times VI sine 40 over 4.9 equals 60 meters. We now rearrange this to give VH equals 60 times 4.9 divided by VI sine 40. We can now call this equation 4, and we substitute equation 4 into equation 3. So basically they're equating each other, so 60 times 49 over VI sine 40 equals VI times cosine of 40. So this whole question is leading you down the path of some complex simultaneous equations because it didn't include much information, and the information just comes from the type of question. Also, the order in which the information was given makes it more complex. There was one piece of information from the start of the projectile motion and one piece of information from the end, how far it went. We rearrange this completely, and we get VI squared equals 294 over cosine 40 sine 40. We can do the calculation of 294 divided by cos 40 sine 40, and then that gives us 576.84, and then we square root this, and we get 24 meters per second to two significant figures. Now you could then go through the process of substituting that back into the whole thing. Woof, that was not super easy. If anyone manages that, well done. These are, by the way, called expert questions for a reason. Okay, question 2 is the first example I'm giving where the object is landing at a different height from its starting point, and as well as that I've tried to make it a little more complicated by not giving you the initial starting information, but by giving you information more related to the back end of the question. So we aren't given the starting angle or how far away the hoop is. We are given the various heights, all based around a ground reference point. So what we can actually do is start by just sort of substituting these heights. Just take 2.0 meters off them all to make life easier, because really the ball's only going up 1.5 meters and then down 0.45 meters, and that's what we need to know. Okay, so we also know that apex, which is 1.5 meters above the initial point, and 0.45 meters above the final point, is 0.5 meters from the goal. So what I'm going to do is start by figuring out the horizontal velocity, and I'm going to do that by which, you're not asked for that, and that's the point. You're not asked for it, but you've just got to realize, what can I find? And that's the first thing I know I can find. And I can do that by working out how long it takes to fall from the apex to the hoop, and then I can use my horizontal velocity being constant to work out the horizontal speed. So if I know the time, how do I do the time? I need to use, I've got something like d equals VIT plus a half AT squared. When you're coming down from the top, the initial velocity is 0, and the acceleration is negative 9.8, and we want to know the time. So the initial velocity being 0 means we simplify this to d equals half at squared, and here's my mistake. You see that 0.5 on the left-hand side of the equation? That's not right. It's 0.45. So I just made an incorrect substitution. I've used the horizontal distance instead of the vertical distance, and it will take me sometime into the next part of the question before I realize that. So let's just see how long it takes me to realize my mistake. I think I make two big mistakes in this question, in fact. I haven't realized it yet. Okay, so next thing anyway we're going to do is to find the horizontal velocity. We're going to assume that the horizontal velocity is constant and the distance covered is 0.5. I think that's when I probably realize it. So the distance covered is 0.5 meters. Here we go. That's when I realized, hang on, I've just used 0.5. That's not right. So go back, figure out where I can substitute it in, redo my calculation, get new number. Which is important. Good that I caught it there, because that means that I can use that time correctly here. So 0.5 meters divided by 0.303 seconds, giving something just above 15 meters per second. Sorry, something just above 1.6 meters per second. 1.6 meters per second is the rounded two significant figure answer. Right, now, that's the horizontal velocity. What about the vertical velocity? Where do I get that from? Well, I need to know the total flight time. Well, actually, no, I can work it out by looking at it from the apex, basically. So I'm going to find these things using the time and or distance to the apex. So d equals 1.5 meters. The acceleration equals negative 9.8 meters per second. We know that Vf equals 0, and we're asked to find the initial vertical velocity. Why do we know that Vf equals 0? That's because it's at the apex, so it's neither coming up or going down yet. And we choose our formula, Vf squared equals Vi squared plus 2AD, which has those four items in it. We substitute in, we remember that the acceleration is negative. We simplify, so 19.6 times 1.5 is 294. We switch the negative 294 to the other side by adding 294 to each side. We get Vi equals the square root of 294, which is 17.146 meters per second. That seems very high. Does that seem very high? That seems very high. That means it's going to go up in the air for quite some time. I think it's at this point that I discover that I must have another error in what I've just done. Hopefully I realize that pretty soon, because surely it's not going up for 1.5 seconds, and if it went up for 1.5 seconds we would expect to have a height of, like 12.5 or more meters, so that doesn't look right. I wonder how long it'll take me to realize that that doesn't look right. And you know what I've done? It was all good until I multiplied 19.6 times 15 instead of 19.6 times 1.5. So Vi squared does not equal 294. Vi squared equals 29.4. And that gives me quite a different answer of, let's see, 29.4, 5.42 meters per second. Alright, so now, again, using my Pythagoras' theorem to work out the total speed. Total speed is the hypotenuse, of course, and the other two sides are the shorter sides of the triangle. So the hypotenuse equals the square root of the sum of the squares of the shorter sides, and let's do that on the calculator, and I get, what do I get? Wait for it. 5.67 or 5.7 meters per second to two significant figures. And I have one last part of this question to do, which is to work out how far from the hoop the netball player was. There are numerous ways to do this. The You can do this in one equation if you wish to, using Vf squared equals Vi squared plus 2AD with the initial and final velocities that you've already figured out, one being negative, one being positive. You can do this, I'm just going back a slide to gather some information to use. You can do this using, as I do in this case, the two times and the horizontal velocity. You can do this with d equals VIT plus half AT squared to find the total time. There are so many possible ways. You can probably use every equation in the book. However, what I'm going to do is work out the two halves, the upward part, not halves, the two times, the time up and the time down. I'm going to add them together to get a total time and then multiply that by the horizontal speed. So I've already worked out the time down. I've never got around to working out the time up, so that's what I'm doing here. Vf is 0, Vi is the initial vertical velocity, A is negative 9.8. Substitute in, rearrange, get that the time up is 0.553 seconds. Then I add the time down, probably flip back to the previous page to find this. So time total equals 0.303 plus 0.553, giving about 8.5 seconds. Sorry, not 8.5. Gosh, I must have been tired when I did this and now. 0.856 seconds. And then the horizontal distance, you can use d equals VIT. Obviously the acceleration is 0, so half AT squared is 0. So d equals VIT plus a half AT squared simplifies to d equals VIT. D equals the horizontal velocity times 0.856, which is 1.6499 times 0.856, which is, wait for it, 1.412 meters from the hoop is where the person is standing. Rounded two significant figures, that is 1.4 meters. Thank you very much if you have got to this point in the video, and even better if you have continued so hard out through this to have completed the expert questions.